The constitutive equation we use for the mechanical problem is Hooke's law. And it basically relates stress to strain. So this is your stress tensor. This is your strain. And you have some tensor multiplication because this guy, which is your elastic stiffness matrix, is actually a fourth order tensor. So we've talked about this and this before. These are what type of tensors? Second order. So you're going to multiply a fourth order tensor by a second order tensor to get your effective stress. And the dimensions are shown here. This is 3 by 3, right? This is, and that's, I mean, this is your Cauchy stress tensor. This is this fourth order tensor, so it's 3 by 3 by 3 by 3, which is difficult to visualize, right? And you will see what we will do about that shortly. And that is your strain tensor, which is also 3 by 3. So we can use something that is known as the Voigt notation to express the stress tensor and the strain tensor in the form of a vector instead of a tensor. So we already know by symmetry that you don't need all 9 components of these tensors. How many components do you need? Without rotating, you just need 6, right? 3 are redundant because it's symmetrical. So we can write out those 6 components in the form of a vector as shown. The diagonal components first, then the 3 off diagonal terms. Same deal here, diagonal components first, 3 off diagonal terms. So because this is now 6 by 1, and this is 6 by 1, both of them are now 6 by 1. Now what does the dimension of this has to be? Remember, you're going to have to multiply a 6 by 6 matrix by a 6 by 1 matrix, or a 6 by 1 vector, to get a 6 by 1 vector. So this has to be 6 by 6. It's worth thinking about the number of components that should have been here originally will be what? 3 times 3 times 3 times 3 is 81, right? 9 times 9 is 81. Now that you've used the Voigt notation and this has reduced to 6 by 1, this becomes 6 by 6. 6 times 6 gives you what? 36. So because of the symmetry in the stress and strain, you now only need 36 elements of the elastic stiffness matrix. And you can perform this matrix vector multiplication, which basically means you take this row and multiply by each item in the strain vector. So C11 times EX plus C12 times EY, this is where we are, plus C13, the next term, times EZ, this next term, and you continue that way until you exhaust, until you get to C16 times 2EZX. And that will give you just the first term here, sigma x. Then you go to the next row, C21 times EX, and you keep adding, and that's how you get all of these. So that's Hooke's law. And you see here it's written out for total stress. This assumes you have no porous system, like you have metals or any other structure. But if you have a porous medium that has fluids in it, then you wouldn't use Hooke's law on the total stress. You would use Hooke's law on the effective stress only, right? We've isolated the part of the total stress acting on the solid skeleton. Important to note that. So I'd explain this, right? 3 times 3 times 3 times 3, 81. Based on symmetry in the stress and strain, you only need 6 components. So this matrix becomes 6 times 6. So you need 36 independent elastic constants. Then it's interesting that there is actually symmetry also in these matrix, in this elastic stiffness matrix, meaning you wouldn't need this, the off diagonal terms, you wouldn't need this, you wouldn't need this. All the off diagonal terms will be unneeded. So if you add the terms, if you count only the terms you need, you are left with 1 plus 2, 2 terms here, right? Plus 3, plus 4, plus 5, plus 6. And 1 plus 2 plus 3 plus 4 plus 5 plus 6 gives you 21. So you only need 21 independent constants to define this elastic stiffness matrix for an anisotropic system. What about transversely isotropic systems? So that means there is an axis of symmetry, and that axis of symmetry is the z-axis, right? Because if you rotate the stress tensor along the z-axis, meaning you are moving the x and the y in any direction, the material properties are the same. Because we explained that in the horizontal direction, the material is the same in all directions, but changes as you go vertically downwards due to layering. So that will reduce this number of independent constants further from 21 to just 5. So you will need only 5 independent material properties to describe transversely isotropic materials. Then for isotropic materials, which I talked about before, you need just 2. And those 2 could be any pair, such as Young modulus and Poisson ratio, or bulk modulus and shear modulus, or first and Lami's constant. Those are typically the most common elastic properties we use. And I'll later demonstrate during the Zoom meeting where you can find the equations to convert from any pair to any other pair. Hooke's law for isotropic materials. So this will now be linear isotropic materials, right? And I said you will need how many independent constants? How many independent constants? Just 2, right? And those 2 in this case are Young modulus and Poisson ratio. So you can see all of this is just using the Poisson's ratio multiplied by this term outside. So this is your stiffness matrix. And I explained all of this while on the previous slide. How do you rewrite the stiffness matrix in terms of the first and Lami's constant? You use the equation I'll show you, which is on Wikipedia. If you Google Wikipedia for Hooke's law, so go to Wikipedia and type Hooke's law, you will see the table at the bottom, and I'll show this in the actual, in the Zoom meeting for the class. The first and second Lami's constants are lambda and mu respectively. So mu is actually same as G, which is the shear modulus. And we'll talk about those in the Zoom meeting. For transversely isotropic materials, like I had explained, there is an axis of symmetry, and in rocks, it will be the z-axis because the material is symmetric. The material is basically isotropic in the horizontal direction. Anywhere in the x or y, the material property is the same. And shales and most reservoirs transversely isotropic. This is what your matrix will look like your elastic stiffness matrix. And yeah, the answer to this is the z-axis. What are the 5 independent elastic constants here? Well, it's Young modulus in the x direction. You see it's the same parameter here. Then in the y direction, that's the second 2. So 1, 2, 3, Poisson ratio in this direction, Poisson ratio in this direction, 4. All right, which other one is new? We already used these. 3, 1, 2, 3, 1, 3, 1, then mu 2, 3. Those are the 5 independent elastic constants. And you can see they're independent because the one in this direction is different from, E1 is different from E3. 2-1 is different from 3-1. And we'll stop here.